Greetings all, welcome back. Today I want to talk about another feature of differential equations which is going to be very, very useful for us when we attempt to solve or to study or to analyze a differential equation. And that is a notion of whether the differential equation is linear or not. Okay, so the definition for this is the following. First, I want to start with a function. So just any function, f, and that function is going to have a number of inputs. Okay, and I'm going to break those up into inputs of type x and inputs of type y. It doesn't really matter, but it just has a number of inputs. I'm going to add a little bit to this, and I'm just going to write this as a vector because it'll just make my life easier and not really, create too much more of a bother. This guy is called linear. And it has to be linear in something. So this is going to be linear in the variables y1 up to ym if it has a certain form. And that certain form is the following. F of x1 up to xn, y1 up to ym can be written as in the following way. Some function of just the x variables, and then a sum of functions really again in the x variables times y sub I. Okay. Now to understand what this means is the following, where the ai of x's, these guys, are arbitrary. Okay. So if we can take a function, and that function is a function of x and y, or x's and y's, and we can always sort of mess around with this function without changing it so that it looks like just some messy function of x, of all the x's, and then a sum of messy functions of all the x's times just a y by itself, and each one of those pieces, those summands, is like that. Then we say that this function is linear in the y's. Okay, now that's a little bit odd, and this is not quite in the text. So this is the reason why we call differential equations linear. So to do a very quick example, here's an example which I'll do right over here on the edge. If I have a function f of x and y, and that function looked like the following, e to the x y plus cosine x. Okay. This function actually is linear in y because the y shows up just by itself in one of the expressions. And no matter what the x's are, it doesn't really matter. It's linear in y. Now there's a reason why we call this. In other words, if we add a sum of two things, if a function is linear, it should equal the sum of the function evaluations of those two things. So that's really the reason why this is linear. This guy is linear in y. It's not linear in x, though, because cosine and e to the x are not linear functions. But it is linear in y. So that should help there. Now, for an ODE, so we're in a position now where we're talking about a differential equation being linear. Let's take the generic nth order differential equation. Now for a generic nth order differential equation in its general form, this is linear as an ordinary differential equation if the following is true, if f is linear in y, y prime, all the way up to yn. Okay. That's when we can tell that the differential equation is linear, when it's linear in the dependent variable and the dependent variable's derivatives, not necessarily the x. So this would have to be in a certain form, and that certain form would look like the following, and I'll put that again in this other color because it does sort of stand out. We should be able to write f as a to the n of x. Remember, x is the independent variable, so it's not linear. This thing does not need to be linear in x. It just needs to be linear in the y's. A sub n x, y to the nth derivative, plus, follow this pattern, that's what the ellipses are, a1 of x, y prime, plus a0 of x, y, and then something off by itself. And we'll call that g. The reason why I'm using a's here and a g here is because later on when we study linear differential equations of this particular form, this is going to be very useful for us. This particular format you're going to see again. So all these bits and pieces here are the bits and pieces, these a's of x's, these functions of x, and then attached to them are some of the derivatives of y. Some of these guys can be 0. It's perfectly fine. This is linear no matter how weird an of x gets and a1 of x gets and a0 of x and gx. It doesn't matter if it's even defined at certain points or anything. As long as I can take this thing and rewrite it this way, this guy is called a linear nth order differential equation. Okay. And if it's not linear, it's nonlinear. Okay. So here's some examples. Here's the first example. Sine x y prime plus the natural log of x, y equals e to the x equals tangent of e to the x. I won't ask you to solve this differential equation, but it is linear, and you can actually. It would take some effort, but we could do it. Turns out we can solve linear differential equations, which is one of the nice reasons why if we can figure out which ones are linear, we do have methods for solving them. This guy is linear because here, I don't care that this is a nonlinear function. It's a nonlinear function of only x, so it's fine. This guy here is also nonlinear. This guy here is nonlinear, and it's a compounded function. It's a composition of functions. But because the y and the y prime are separated out in this way, this is a linear differential equation. Okay, that's one. Here's another. Y double prime, this one's a little bit easier to see, plus xy prime plus sine y equals 0. This kind of looks like it's in this form or in this form, except for this part here, the sign of the dependent variable, the unknown function. That guy actually is nonlinear, so this guy is not linear. As an ordinary differential equation. So we actually call that nonlinear. And that's a problem. A lot of very wonderful mathematical models are nonlinear in nature, and that's fine. It's just that it makes it much harder to solve them when they're nonlinear. And then the last example is this one. Y prime, y double prime, plus y equals 0. And it turns out, yes, y shows up off by itself as a summand. Y prime is there, and there's no function of x. The function of x in there is 1, is the function 1. Y double prime is there also, but the fact that two of the y variables, two of these derivatives are multiplied together means that this is nonlinear. Remember, they have to be separated out by summands, basically. where the x's can be as weird as you like, but you can't have two y's attached to each other. You can't have the square root of y prime. You can't have y prime squared. You can't have sine of y, e to the y, that kind of stuff. You also can't have two of these derivatives multiplied together. So this is nonlinear also. There'll be plenty more examples to work with. It's always the case that when you're presented with a new differential equation, determining its order, determining basically whether it's linear or nonlinear, these are mostly by sight. And once you get a little practice, it becomes pretty easy to see, but it's always something you can sort of work through even if you're not quite clear. And after a while, it becomes sort of second nature. Okay, so I will leave you for that for now. And we will talk to you again very, very soon.